like a regular grating. It's a dynamic grating because the laser beam is running. So the grating is made every second. It's not fixed. It's like a water running in the river. You step into the river. So this makes a dynamic grating. Now look at, next step is finished. Dynamic grating. You see the funny point. When you have a dynamic grating like this, and when I send a wave, you have a wave reflected from this. Since it is a grating, it will produce many patterns here and here like this. Because of the grating effect of this will have spatial, again look at this, spatial variation of refractive index. Immediately you will see, where you will get, at this point you will have maximum intensity. If you have maximum intensity, the refractive index becomes non-linear. It goes too much, changes. When there is such a dramatic change in the refractive index, it produces a wave front which is phase conjugated. Understand? All that is important is produce high refractive index changes. High refractive index changes is made by high intensity beam. In the Raman laser, we focus it. Look at it, we focus like this. Then we produce high intensity and changes in the refractive index. Whereas in this case, you don't have to focus it. The two beams interfere, and maxima you will have more refractive index. Here, less refractive index. Such a modulation of high refractive index, low refractive index produces phase conjugation. People have succeeded this kind of phase conjugation, using Raman laser, Brillouin laser, and this kind of dynamic grating. In this case, this is a Heaney laser, look at it. This is a Heaney laser, this is a Heaney laser, or
same laser?
Same laser. I start from the same laser. I split here, I split here. I put on one mirror, I can get it. Then what I do? I give the schematic. You will understand. I start with Heaney laser. Put one mirror, go. This is another. These two interfere. So I have made a grating here. Next step. Now look at it. I send an argon ion laser. Expand it. Put my object, a distorted object. It goes and it comes back. This undergoes phase conjugation at this. It becomes like a phase conjugate mirror. That's all. So, look at this. If this is an object with aberration, what I see final is a pure image. Let me repeat. This particular object is a glass piece, okay? But it has certain aberration. For example, imagine this a diamond with some black spot, understand? So light will pass through the diamond carrying the black spot. after passing through this one, when it comes back, the black spot will be removed. Oh, sorry, it should come back here. It comes back, and then when it comes back, the black spot is removed. On the image, it's not, the spot is not removed. The image will be pure. It will look like a pure black spot. Sorry, pure diamond. Understand? The crux of all this one on one point. There is a very good equation for this. The refractive index, it all depends on intensity dependent refractive index, which is given as this. This is the equation. Refractive index is given as 1 plus 4 pi chi naught. Excuse me.
Hello, how are you?
Yes, sir. 4 pi chi naught plus 3 pi chi 1 E naught square plus something. Okay?
Sorry, okay. 1 plus 4?
1 plus 4 pi. 4 pi chi naught is a susceptibility which you are studying.
Yes.
This is 3 pi chi 1 E naught square. Now what is this E naught square? This is the intensity. That means the refractive index becomes a function of refractive intensity. And such a changes in the refractive index produce phase changes. It produces a negative phase change, that's called the phase conjugation. Understand? You can do in any way like this one. You can do changes the refractive index by this method or by focusing for Raman days. Understand? Only these are two methods. So I stop with this one. In the next lecture we will start with self-focusing. I can explain self-focusing straight away. 1 minute. I'll finish that also. Phase conjugation and self-focusing. Let's finish the self-focusing. Both I will show next lecture. Self-focusing. The equation shows this will be root of 4 pi chi naught plus 3 pi chi 1 E naught square plus something also is there. Now what I am going to do, I have water or any liquid. I send the laser beam like this. No, like this. Then look at it. This is the midpoint, this is the side of the beam. Then this will go straight like this, but as it goes, when it goes here, the refractive index increases because I send a high power in laser beam. When the refractive index increases, it will not go in a straight line, it will go like this. Because greater the refractive index, it will be bending towards the normal, right? Let me explain. Forget this one. I have glass. Imagine I send the light. Then the refractive index is 1.5, let us say. Then this is theta 1, this is theta 2, this is sine theta 1 by sine theta 2, right? That's a refractive index. Next thing. Now, let me say this is 45 degree. How much will be this? Calculate. theta 2 will be sin theta 2 will be in fact 1.5 sin 45
It will be 2.
1.5
1
sin theta 2 will be it should be 30 degree 35 degree.
minute. 28.
28. Okay. Now this will be 28. Okay. Now go to the next step. I take another material n is equal to 1.7. I do the same experiment. What will be that?
The same angle 45.
Same angle. I do same thing.
Uh, 25 nearly.
25. Now that's all what I need. Look at it. I have some glass. If the laser beam comes like this, if the laser beam is strong enough, then the refractive index increases for that glass. Understand? Since the refractive index increases, instead of going straight like this, it will bend more and more like this, more and more like this. Then the beam, instead of coming and forming here, it will focus here, right?
Okay.
This is called self-focusing. The self-focusing means the beam focuses by itself because of high intensity. So it is an intensity dependent focusing. Which means like this. Look, imagine I send the laser beam like this through an optical fiber, and then the beam becomes more and more focused throughout. Because of the focusing, you will have many nonlinear effect when you try to pass through optical fiber, which we will see later. So, next important thing is if the intensity is still high, at this point it will break. The intensity is so high, the material property changes so badly that the light cannot pass through like this. It will go damaged. It will produce lips. You understand? It becomes laser-induced breakdown of the material. You know what's lips? We have studied?
Yes, yes.
You have studied what's lips? Laser-induced breakdown. I think last semester we studied.
Just take experiment with you.
Yeah. So, when the intensity is so high, you will have lips.
Electric field will be very high.
Electric field will be very high, it produces a plasma.
Right.
That's all. So these are the two major problems for high power laser application. Non-linear properties change, intensity change the refractive index. This is the major non-linear phenomena. Because of the change in the refractive index, you have self-focusing and phase conjugation. That's all. And lips or plasma generation. These are three things. Since we have studied lips earlier, I will not go into the detail. The next lecture, tomorrow you will have the test. Next lecture I will show you Raman laser. I will show you self-focusing. I will show you breakdown also. Yes, tomorrow. Tomorrow I will be
After
there.
prayer,
After exam?
Yes,
12.
prayer. You can after prayer. I will be there in the lab tomorrow. Anytime.
The exam?
12 to
The
1:30.
exam from 12?
After prayer.
The exam?
Yes, 12:30 to same 1.5 hours. That's okay. Okay.
Okay, thank you.
See you
Thank you.
then.
يا زلمة هذا يا رجل